transfer lines in our lab and some studies thereon, and we'll end the talk with the conclusion. So before going further ahead, let me speak little about cryogenics or the introduction to cryogenics for the people who might have missed the past lectures, which Professor Kasturangan has given a very good introduction on cryogenics and superconductivity, and you are now gained a lot of knowledge on cryogenics. I'm sure it must have given you ample knowledge on this cryogenics as well as superconductivity. But for the people who have missed the past session, let me give little introduction and without taking much time. So the cryogenics is derived generally from two Greek words, cryos and genus. So cryos means ice cold and genus means generation or production. So literally cryogenics deals with production or generation of icy cold. So cryogenics is the science and engineering for production and utilization of very low temperatures. But also we can produce low temperatures by refrigeration system. But there is a dividing line to separate refrigeration from cryogenics. As per the National Bureau of Standards at Colorado, Ohio, in USA, cryogenics deals with temperature below minus 150 degrees centigrade. And this is a equivalent interesting number is 123 Kelvin, which is very easy to remember, 123 K. So if I go below this temperature, then cryogenic starts, and above that, with refrigeration systems, one can achieve lower temperature. Nevertheless, it is very difficult to go to below minus 150 degrees centigrade by refrigeration systems, but if you can go also, it will be very complicated process like cascade refrigeration and so. And so many interesting things happen once you go to below minus 150 degrees centigrade. People earlier days what they're thinking some permanent gases means the gases are permanent in nature and cannot liquefy like nitrogen, oxygen, argon, hydrogen, or helium. Cannot liquefy. That was the thinking. But if you go below this temperature, we can easily liquefy all these gases. So below this temperature, these all permanent gases can be liquefied. And in this realm of temperature, if you see, then rubber becomes as brittle as glass, and that is the basis for cryo-grinding up of PVC, plastics, polypropylene, which is really difficult to grind in conventional mills, and if you are grinding also, the quality of these materials deteriorates. So in that way, cryo-grinding helps a lot, and that is the basis for, that is the technology for cryo-grinding of PVC by cryogenic means. You can easily grind this, and this very good introduction has been given by Professor Kasturangan. Again, what I mean to say, that below this temperature or in this area of cryogenics, you will see that metals and alloys change their properties. Some metals and alloys means all the metals and alloys, they lose their resistivity, or resistivity decreases with the decrease in temperature. And at a certain temperature, some metals and alloys becomes superconductor, meaning that there is no resistance at all. And this because the basis for this maglev trains, MRIs, this magnetic resonance imaging, magnetoencephalography, all this is possible because of this cryogenics, and superconductivity plays a crucial role there. And also by superconductors, by superconductive technology, you can use power generation, and the power is generated, stored, and transferred or transmitted. And that is very effective. Of course, the technology is somewhat different and costly, so one have to consider both application as well as cost involvement. And the living cells pass a state of suspended animation, where all these biological reactions are almost stops. And as long as you store all these biological specimens or organs in special design containers, and your cryogens are there, then there is absolutely no time limit to store all these material or specimens or organs. So you need special container and cryogens so that it can be stored as much time as you need for it. Okay, with this, I'll just leave an introduction to cryogenics. Then let us go to properties of some cryogenic fluids. Here, I'll emphasize on 2-3 parameters related to the properties of common cryogenic fluids. So, the common cryogenic fluids, or which are known as cryogens, are oxygen, argon, nitrogen, neon, hydrogen, and helium. All of us know oxygen is available 21% by volume in the atmosphere, and nitrogen is 78%. Argon takes another place, which is around 0.93%. Neon, of course, is very less, and hydrogen 40 to 50 parts per million, and helium around 5 parts per million in the atmosphere. And if you see all the boiling points of these cryogens at 1 atmosphere pressure, so you can see that start with descending order of boiling point. This oxygen boils or it liquefies at 92.2 90 Kelvin almost, the boiling point at 1 atmosphere pressure. And similarly, argon is 87.3, nitrogen is 77.3 Kelvin, neon is 27.1 Kelvin, and hydrogen, the boiling point is 20.3 Kelvin, helium is 4.2 Kelvin, and the numbers given in the bracket in blue color is the corresponding Celsius degree Celsius temperature. Okay, and I will emphasize on latent heat evaporation and the volume expansion ratio, including the density of these reagents. If you see the latent heat of evaporation of water is around 2,255 kilojoule per kg. Whereas for all these cryogens, this latent heat of evaporation is very low. It is for oxygen 213 kilojoule per kg. For argon, it is around 162 kilojoule per kg. Nitrogen 199.3 kilojoule per kg. For neon, it is 85.9 kilojoule per kg, and for hydrogen, it is 443 kilojoule per kg, whereas helium is 20.9 kg per kilojoule per kg. And the density of these cryogenic fluids also, you see, is varies a wide range. Oxygen is slightly slightly denser than water. Water is having the density of 1,000 kg per cubic meter, whereas oxygen is 1,141 kg per cubic meter. Argon is 1,394 kg per cubic meter. Nitrogen is 807 kg per cubic meter. Neon is 1,206. Hydrogen is 71, and helium is 105 kg per cubic meter. So what you can see here, the latent heat of vaporization is very less, and density there is a lot of variation. Hydrogen, you can see, is almost 14 times less than water. Helium is almost 1/8 of water. And the another point is that what I say that latent heat evaporation of these cryogenic fluids are very less. That means for the same amount of heat input, 1 liter of liquid argon vaporizes 10 times faster than water. This is a relative comparison. And liquid nitrogen vaporizes 14 times faster than water, whereas liquid helium vaporizes 100 times faster than water. Apart from this low latent heat of vaporization, it has another peculiar property which needs special attention for storing and transport is the volume expansion ratio of cryogenic fluids are very high. Just see, this table gives the idea that when oxygen, 1 liter of liquid oxygen, when vaporizes vaporizes and to room temperature, that is 300 Kelvin at 1 atmosphere pressure, from 1 liter of liquid you can get 797 liters of gas, almost 800 times, and argon is 779 liters from 1 liter of liquid argon. Nitrogen is 646 liters from 1 liter of liters of gas from 1 liter of liquid. Neon is 1341, hydrogen 788, and helium is 701 liters of gas from 1 liter of liquid. So, as a thumb rule, 1 liter of liquid cryogen expands to 700 times. This is the approximate value, 700 for helium, and nitrogen is almost 700. So that is the minimum, and it goes to 800, and sometimes it goes to more than that. That is neon, except neon. Between here, that is 1341 liters of gas you will get from 1 liter of liquid. So such behaviors are of concern as rapid vaporization because of low latent heat and a large expansion ratio may lead to rapid pressure building. This you have seen the demonstration by a video given by Professor Kostirangan, putting some cryogens in a plastic bottle and putting it for some time. And because of low latent evaporation and large expansion ratio, so you could see how it has just busted or exploded. So one must take consideration of these factors while designing a cryogenic system, including the safety measures. So these needs that you need special storage and transport system, including the safety measures. So you need special storage and transport systems because these cryogenic fluids are used for a wide range of applications. If you see, actually, people generally don't realize that really this much applications are in all fields of our life, starting from in any industrial or laboratory application, starting from manufacturing process to space, transportation, power generation, food freezing, cryo treatment, all that things. And under manufacturing, the main because of cryogenics, all this possible, which people generally don't realize. Ammonia is a byproduct because of this nitrogen is used there for making ammonia, and by cryogenic means it is produced in tonnage basis in tonnage distillation columns or tonnage plants. And then steel making is another important factor where you need to maintain the quality of the steel by oxygen blowing. In the blast furnace, they maintain the quality of the steel by taking the percentage of carbon, and that what they do, they are inject oxygen to this molten slag or molten metal of iron. Then they control the carbon percentage. And steel making is another important factor, and also cold stretching of a high pressure gas cylinder by cryogenic treatment enhances the yield strength almost 4 to 5 times. And we are all aware of acetylene welding and sealing fitting in mechanical applications. Apart from that, in rocket propulsion, where people we use, everybody is aware that now we use liquid hydrogen and liquid oxygen for rocket propulsion. And this is so because this cryogenic fuel and oxidizer gives maximum thrust, that is the amount of thrust produced for burning kg of fuel for a second, that specific impulse for this cryogenic fuel and oxidizer is maximum compared to all other fuels used in the rocket propulsion system, compared to whether it is liquid like hydrogen or alcohol or any solid propellant. Okay. Then also in space simulation, we make these chambers simulate the space condition to test all these space components in healthcare. MRI without MRI without nitrogen and liquid helium, it is not possible. I have told that MEG and cryosurgery also is another important area nowadays. Biological systems for storing these biological specimen and organs, power generation, storage and transmission, then food freezing and cryo treatment of metals to enhance the true life, and transportation like magnetic levitated trains where you can achieve a speed of more than 500 kilometers per hour. And this is in use in some advanced countries, and then in other applications of these cryogens are semiconductor industries, inert packing. Every day all our food packets are coming with nitrogen packing or inert packing. Then cryo study the properties of molecules or electrons. So there are a wide range of application, and indirectly in all fields of our life, these cryogens are being used. So we have to, an advantage that we have to, when we liquefy this gas to liquid form, or this gas when get liquefied, then the volume is reduced to almost minimum 700 times, and it is easy to store. But in the same time, one has to take care of a special consideration to store these liquids so that after liquefaction, the important factor is how to store this so that less boil up and longer period of storage will be there for all these cryogens, and with adequate safety. So while designing all the cryo systems, you have to think of the minimum heat transfer, or you have to minimize the all modes of heat transfer like conduction, convection, and radiation. So that is the need for this storage and transport systems. So now let me speak about first on storage systems, then we'll discuss on transport systems. So based on the storage system, classification of storage vessels depends on many factors. One of that are given many aspects. First one is depending on the capacity of these cryo vessels. They are divided into large vessels, which is of the capacity of 1 to few tens of liters, and large vessels up to 1 lakh liters or more. And this right side figure shows a container that is from inox, and it is as the level indicates TA55. That means this is a container. It's a portable container of liquid nitrogen, and which can store 55 liters of liquid nitrogen. And this detailed cross section will come next. And depending on the performance, they can be classified as low performance vessels where it can cryogens can be stored, and it just gets boiled off in few hours, where the insulation is not of a best quality, and there either rigid foam or fibrous insulation is used. And high performance vessels where the percentage evaporation or the boil up of the cryogens is less than 0.1% in a day. That because of that longer storage period of cryogens, and these vessels are with a multi-layer insulation, that is vacuum plus mylar. This shows the cross-sectional view of a cross-sectional view of a potable dewar, and I'll just come to this after finishing this. Let me give the detail of this potable container. This essentially consists of a outer vessel, what you can see here, and an inner vessel. Of course, this is for specimens where there are canisters where your biological samples or any samples which you want to store, you can store. Otherwise, if you want to just store cryogens, then these canisters are not there. It is the inner vessel, outer vessel, and the interspace between this inner and outer vessel is the vacuum with super insulation. You can see here, this is the cross-section view, this is the outer vessel, this is the inner vessel, and here I can store my cryogen or these specimens when canisters are there, and then of course, we evacuate and put the mylars, multi-layer insulations are all radiation shields, which we'll discuss in the latter part of the presentation. And this is the vacuum port to evacuate or take out all the gas molecules in between these two, or the interspace. And here, this is put with multi-layer insulation, what I have seen at this point. And then this is the evacuating nozzle of the evacuating port. Then this is fitted with a loose cork, just that the vapor, whatever is forming because of some amount of heat transfer to the cryogen, that escapes through this. And this is a loose fitting cover. And especially these corks are of low thermal conductive material. But one thing one has to remember, that an important point, that all these dewars, or these small portable dewars, the inner container is supported only from the neck of the outer container. And in between these two, we use fiberglass neck or the fiberglass tube for joining the inner container to the outer container, so that heat transfer is minimum. And of course, you are having slits with this cork, so that if at all any vapor is getting, some amount of vapor will be generated from this liquid because of some heat transfer. We cannot completely isolate there or stop the heat transfer to the cryogen, so that escapes easily through that slits. So this gives the detailed construction of potable container. And depending on capacity and performance, I have already told. Let us see the other categories, how we classify these containers. Based on shapes, there are different type of cylinders, like cylindrical cylinders, or you can see conical cylinders, cylinders with some cone arrangement on the top especially. Then spherical shapes for very large quantity of cryogen storage, and sometimes combination of both, like cylindrical with a conical is available. Then combination of like cylindrical, conical, or spherical. Then depending on the pressure building, these containers can be divided into small dewars are generally unpressurized, and there is best pressure building, either it will be unpressurized or pressurized. And all small containers are generally unpressurized containers, and while dealing with this type of containers, generally they fill and pour the sleeve by hand and pour it, but one has to be very careful dealing with these containers. As I told, this inner container is just suspended from the outer container, neck of the outer container, without any support. And these pressurized containers are of a medium to large vessels. This shows the transportable cylindrical vessel with some descent of different, it may be elliptical, it may be spherical, it may be hemispherical, like that. And this shows the instrumentation part. This is a cylindrical container, vertical container for cryogenic application from Cryo USA. This is of 240 liters capacity, and if you see the instrumentation part, there is a part which measures the liquid level. One part is connected to the liquid, and the other part liquid level, and so other part is connected to the vapor space. This is the level gauge. And then this can measure depending on the differential pressure and the level of liquid, because the weight will be different for different levels. So that way you can measure the level of the liquid inside the inner container. Then the pressure control valve is there to regulate if you want to pressurize. This is a pressurized container. Some part of liquid will go and then comes to atmosphere and gets boiled off. Because of large volume expansion, again it can build pressure for runout. That we'll discuss in subsequent slides. And you will have different valves like for filling and draining, venting, and then some pressure gauge to measure the pressure. And the safety part, which is very essential, this is the relief valve. One part only is in here, and this is the rupture disc. If the relief valve is not working, then the rupture disc can burst, and all the pressure can be, if the pressure is more than the design pressure, and if the relief valve is not working, it gets actuated, and then it bursts. They call it bursting disc or the rupture disc. So this gives the idea of classification of different type of cryogenic viewers or containers, including small to very large capacity. And after that, saying so, let us see the basic design of cryogenic vessels. Because when I know that I have to make special containers for storing all these cryogens, then I should know how to design these things. So everybody or all of us know about thermos flask. Actually, they are the vacuum insulated flask which we are using for our everyday life for storing hot fluids like tea, coffee, milk, or keeping cold items. So it can easily store or maintain the temperature either hot or cold for longer period. So when this cryogens, people try to liquefy all these cryogenic fluids. That time, Professor James Dewar, he was a professor at Cambridge. Actually, he's a Deutsch physicist, chemist, and he was working at the University of Cambridge. While attempting to liquefy oxygen and hydrogen, which he had assessed in 1891, he could able to liquefy oxygen. And when he wanted to store it, he needs special containers to store it. Without that, it just gets boiled off once it comes to the atmospheric temperature. So after liquefying this oxygen in 1891, he tried to develop some special containers which can store all these cryogenic fluids. And then in 1892, he developed a double-walled vacuum-insulated flask, which you can see here. I'll come to that later. And when the cryogens stored in that container, the evaporation rate drastically reduced to 30 times compared to uninsulated. So that is a breakthrough for this design of cryogenic containers. And though he has invented this double-walled vacuum-insulated flask, a person named Thermos, who took patent for this, then made these containers for practical application, and because of this, these containers are known as thermos flask. And here this figure shows the Professor Sir James Dewar is presenting his invention or the discovery of a double-walled glass vessel, double-walled vacuum insulated flask to the Royal Institution of London, and later he became the Fellow of Royal Society. So that is the basis for cryogenic storage vessels, and the concept of Dewar is now used for design all these vessels. And you see that what I've seen earlier with the double-walled vacuum insulated, it is all other containers for cryogenic applications. You can see there is the inner container which stores the cryogens inside it, then the outer vessel which forms of the vacuum jacket. This is the outer jacket. Then the insulation between the interspace, the outer in between the inner vessel and the outer vessel. The inner vessel sometimes called as product container, and the outer vessel also known as the vacuum jacket. And the interspace insulation that may be of different categories, which we'll discuss the insulation part section. It may be powder, fibrous metals, vacuum, or both vacuum and milers, which is known as multi-layer insulation or the super insulation. Then these containers, you'll see there's of course a manhole. This is a big size container, and the accessibility should be there for repairing or doing the activities. So it's a manhole, and I have told it's the outer vessel. And the fourth one is the diffuser, vapor diffuser and vent. These are needed for venting the gas and also sometimes pressurizing the container. So pressurization of the inner vessel and venting the vapor what is getting generated in the container. Apart from that, another part one has to consider is the oilage space. So unlike all other containers, the cryogenic containers are designed for 10% of vapor space. That means the liquid should be filled up to 90% of the inner container, keeping some 10% space that is known as the oilless space. And it is provided to reduce the vapor pressure increase due to the heat inlet when it is coming from the outside or from to the cryogen. So this diffuser, this oilless space also helps that the gas, warm gas is directed away from the surface because diffuser is open at the top, so it is not directly some the vapor is coming from pressurization, for example, then it should not directly contact to the liquid surface, so that much evaporation takes place. That also take another important role, this diffuser, to reduce the condensation of the pressurized gas and also boil up the liquid cryogen. So you need special drain and fill lines because you want to fill the inner container with cryogens, and whenever you need, you have to also extract. So this is the fill and drain line that is a part of these cryogen systems, and then anti-slush baffles are used for transportation vehicles. Apart from that, you can see there is some stiffening ring which supports the container. And in the inner support, inner container is supported in the outer container. So this is the part of this cryogenic container. So one has to now see, once I know that this is the concept what has to be there in the storage QR or the storage vessel, then I have to now design all parts so that I'll be able to successfully store cryogens. So the first part is the inner vessel design, and this inner vessel, what I have seen, filled with liquid here is given the cross section here, and these are designed based on the American Society for Mechanical Engineers boiler and pressure vessel code section 8. Okay, and also it also maintains the British Standard Institution standard 1500 or 1515. And the design of this inner vessel should be such that it should take the internal pressure inside the container, and then the weight of the liquid, also the bending stresses, whatever is happening, occurring because of load. Then the material selection is another important parameter for container design. So the materials should be compatible with cryogenic fluids, generally stainless steel, aluminum, this monel, that is nickel and copper alloy, and copper sometimes alloy are used, but most most of the cases, the inner container is designed with stainless steel, but the inner vessel should be designed with wall thickness as less as possible, because first thing is that it will have, if the thickness is more, it will have more thermal mass, and you need more liquid to cool it. Weight is another factor of that container. Then also, it should, when the thermal mass is more, you have to spend more liquid or cryogen to cool it down, and also cost also is another factor. So all this has to be considered while designing this inner vessel of a cryo vessel. And steeping rings, of course, has to be designed so that it will take the support of the weight. Generally, this angle of the steepening ring is in the order of 72 to 90 degree for good support structure for inner vessel in the outer vessel. Then the minimum wall thickness one has to find out when I select the material. Then I should know what is the minimum thickness needed for this inner vessel. So as per ASME code, again, this minimum thickness for cylindrical vessels, what you are seeing here is given by T, that is the minimum thickness. That is P, design internal pressure, plus the inner diameter of the inner container, divided by 2 into let's say the allowable stress multiplied by holding efficiency minus 1.2 into design pressure. Okay, and if you take in terms of the outer diameter of the inner vessel, that is D0 is the outer diameter of the inner vessel, which is equal to D plus 2T, then you will end up with this equation, that is T into D0 by 2 into SAW plus 0.8P. And after making this thickness, or after arriving at this thickness of this inner cylindrical vessel, I need the thickness of this hemispherical or elliptical or spherical end. So that is given by the equation. This thickness of this spherical or hemispherical head should be P equal to P into D diameter of the vessel into K. K is a constant that is given by this equation 1 by 6 multiplied by 2 plus D by D1. D1 in minor diameter of the elliptical head. If it is elliptical head, then you have to go for that. This K value we can get from here, and from this equation you will find out the thickness of the head of this inner container. Okay, so of the inner vessel. So you need the thickness. You got the thickness. You got the thickness of the cylindrical vessel. Next is the thickness of the head, what is at the end of cylindrical vessel. So with that, you need these two parameters to design the inner container, and then the outer vessel design. The outer vessel actually don't act on the internal pressure does not come to play there, because in between the inner vessel and the outer vessel there is vacuum. So the outer vessel is generally the pressure is or the load on this outer vessel is the pressure, atmospheric pressure. So it don't fail because of excessive stress, but it fail due to the elastic instability because of this pressure what is working, atmospheric pressure working on the outer vessel. And so we have to consider the collapsing or the critical pressure, because whereas the inner vessel we have considered for the internal pressure, and now this collapsing or critical pressure, from this equation we can find out the thickness of the outer vessel. And for long cylinder, this is the equation PC, that is equal to pressure, critical pressure, which is equal to 2 into Young's modulus into multiplied by P by 0, the outer diameter of the outer container or the vessel, to the power cubic power, divided by 1 minus mu square, where mu is the Poisson ratio. And the when I am writing long cylinder, the long cylinder is defined by when L by D0, that is length to diameter ratio, is greater than 1.140, again multiplied by 1 minus mu square whole power 1 by 4, whole multiplied by D0 by 2 to the power half. And if my L by D value is greater than this, that is known as long cylinder, and I can use this equation to find out the thickness of the outer vessel. And if it is a short cylinder, suppose I am getting this L by D ratio less than the value at the right side, then I have to use this equation, which is the critical pressure, which is equal to 2.42 E into D by T to the power 5 by 2, divided by 1 minus mu square, whole power 3 by 4, again whole multiplied by L by D0 minus 0.45 T minus T0 half. So with this I can find the, this is the thickness of the outer cylinder for short cylinders, and the collapsing or the critical pressure, again it is the hemisphere, or the end is either hemisphere or elliptical, and again it is the atmospheric pressure is working on that. So the collapsing pressure or the critical pressure is given for this hemispherical or elliptical head as PC for 0.5 V whole multiplied by TS, that is the thickness of the head, divided by RO, or the outer radius of the head, to the power 2, is divided by 3 into 1 minus mu square whole to the power 1 by 2. With this, I can now calculate the outer vessel thickness as well as the thickness of the sphere or the elliptical head. And generally, for all these, we consider factor of safety as per the SM code 4 is used. So now I have designed the inner container or the inner vessel, then the outer vessel. Next is the after designing the inner and the outer vessels, my next step will be to design the suspension system to support the inner vessel within the outer vessel, and that also these suspension systems are given here, and this suspension system also carry the weight of the inner vessel along with its content, liquid content, including the dynamic load, because and if the suspension system is not good, this inner vessel will just toss to the outer vessel and nullify the effect of insulation. So again, direct convection heat transfer will take place from this outer vessel to the inner vessel, and you are landing up in problems, so that you cannot store the cryogen, or if you are putting the cryogen, immediately it gets evaporated. And the commonly used suspension systems are high strength stainless steel tension rods, what is given shown here, and small high strength rods, tension rods, then saddle band or metals or plastics, then plastic compression blocks also be used, also compression tubes as shown in this figure. It is like high strength tension rods and compressible tubes as shown in 3, and sometimes also they use wire cables or chains to suspend the inner vessel in the outer vessel. Okay, this is the suspension system for cryogenic system, and all these suspension systems would have low thermal conductivity, and because of that, materials, when we are thinking, it should have less surface area as well as less thermal conductivity. So that way we have to design all this suspension system. Then this shows a typical support bracket for suspension system of a cryogenic vessel. You can see here, this is a support rod from the outer vessel to the inner vessel, and the inner vessel, this is the surface of the or the thickness of the inner vessel that is connected with a pad, and the pad is extended by some support bracket. This is the bracket, and this bracket is held by the support rod from the outer vessel, and you can see here that where the contact is taking place between the outer to the inner vessel, because this is a heat carrier. So that time you have to use some plastic or some very low thermal conductivity washer is being used, so that the heat transfer will be minimized from the outer cell or the outer vessel to the inner vessel. So this shows the typical one support structure for supporting the inner vessel in the outer vessel with less heat transfer from the outer vessel to the inner vessel. That is the, and the heat transfer across the support system or the support rod is given by this equation: Q equal to KMA is the area of cross section of that rod, and TS minus TC, that is the temperature of the warm end minus temperature of the cold end of the inner container, divided by the length. So that way you can calculate how much heat transfer is taking place through the support structure. Then after supporting the inner vessel in the outer vessel, next thing is to see the piping system to fill liquid cryogen from the in the inner container, or to remove these cryogens or the liquid cryogen fluid from the inner vessel. Also, in the piping systems, counter venting of this vapors, what is being generated from these cryo fluids, and if this piping should be properly designed so that the heat transfer along the pipe should be minimized so that the boil up of the cryogenic fluids will be less. So while designing the piping system, there are different arrangements which we'll discuss in the next slides, next few slides. And you can see that this piping should be as long as possible so that your heat transfer is minimized, means the heat resistance or the thermal resistance should be less, and also this should be thin walled pipes so that the again cross section comes down and your heat transfer also. The idea is that to minimize the heat transfer, minimum heat transfer to the cryogenic fluid. So that way we have to design the piping system, and generally scheduled pipe, these are all thin walled tubes, or if it is not, if your calculation is more thicker than scheduled pipe, then you have to go for scheduled pipe, and this is of stainless steel, and generally stainless steel SS pipes used for this cryogenic fluids. And also while designing this piping system, one has to consider the thermal contraction and thermal conductivity of the material. Of course, because other materials should be compatible. So in that way, as I told, stainless steel is generally being used for all these piping systems in cryogenic vessels. Then let us discuss all this different type of piping arrangement, and this is showing a commonly used multi-layer insulated vessel. This is a common type of piping system for filling liquid nitrogen or draining liquid nitrogen, but it has a certain long length of pipe is obtained between the warm outer vessel and the cold inner vessel by extending the vacuum space. And this is the vacuum space which is extend from the outside here to the almost end of the pipe. But this is not that preferred because you need other arrangements like some fill and drain line, and this is the so that also we'll see that maintenance also is very difficult. And the second type of arrangement is not at all advised for cryogenic vessel design or the piping system in cryogenic vessels. This is a poor arrangement because a lot of heat transfer directly takes place from the ambient to the cryogenic fluids. Because of that, condensation of vapor will take place along the top surface of the line, and then this liquid will get flow along the horizontal line, and again so heat transfer will take place, and heat will get transferred from the inner vessel by boiling condensation phenomena, and it has no arrangement for thermal contraction. So because of that, this generally don't use, and it's a very bad design. You see that a lot of heat transfer can take place, whereas the previous one is having at least a vacuum system. Okay. So the third type is the arrangement with some vertical rise and some bellows which can take care of the contraction, because the other two, they have no provision for taking care of the thermal contraction. As I told, in the piping system, one has to also consider the thermal contraction part of this piping while used for cryogens. So here you can see that there is a vertical rise and expansion bellows for this third type of arrangement, but vertical rise in vacuum space is used to prevent the convection problem, as you have seen in the second case. But the expansion bellows are used to care of the thermal contraction, but it is in the vacuum space. So there is problem for reliability issue, and if leak occurs, then it is very difficult to repair, and also will be costly affair to cut off on the outer vessel, and it is difficult. So the last one is the best piping arrangement for cryogenic fluids. This is having this vertical rise as well as the bellows to take care of the thermal contraction of these pipes, but these bellows are at the standoff region, the standoff region in the outer cell, where you can put these bellows directly to the outer surface of the outer vessel, so that it is easy to repair, and vertical rise also prevent percolation of liquid within the line. So this is the best design for piping system for filling and draining the cryogens from the inner vessel. So next to the so this is the minimum thickness. As you know, it is also very critical. So from this equation, T equal to P by D0 divided by 2 SA, that is the arrived stress plus 0.8 design pressure. That way you can calculate the minimum wall thickness of the piping. But as per your calculation, you have to go to the nearest schedule, because that is only available in the market, and you have to fix that. After designing the piping system for filling and draining line, I should have some arrangement for taking out or pressurize the inner liquid, what is there in the inner vessel, to bring out. So there are generally three methods which are commonly used to force the liquid from the inner vessel. First one is the self-pressurization of the inner vessel, then the external gas pressurization of the inner vessel, because that contains cryogenics, and by pump transfer. That is also another method, but these are different applications. Depending on the application, these three one has to consider. So in self-pressurization is done by removing some part of the liquid from the inner vessel. You can see this is a container, this is a double walled cryogenic container of 1,000 liter capacity, what is in use in our department. So what you can see is the outer vessel only, and with some heat exchanger. What I am telling that during self-pressurization, you remove part of the liquid from the inner vessel, and take, because it is at different temperatures. One is at cryogenic temperature, other one is at room temperature. These pipings are at room temperature. So once you open the valve, then liquid from the inner container will come to this vaporizer or the evaporator, and here it is ambient temperature that will act as a whole heat source. And with that, this cryogenics will boil up, and it passes through series of heat exchangers. And after going that, it again goes this boiling the liquid in the external vaporizer, again goes back to the vapor space or the oily space of the inner vessel, and it pressurizes the liquid so that you can open the valve where you want to drain the liquid. Okay, this is for pressurization, and for draining the liquid, you will have another valve. Apart from that, also one can use external gas pressurization to this inner container, so that you can introduce high pressure from an external source like compressed gas cylinder, and also remove some portion of liquid from this. That is one way, and otherwise remove some part of the liquid from the inner container, and instead of this external evaporator pressure, we take to a pressure building unit where they can also vaporize it by means of some electrically heated vaporizer, so that it gets more heat rather than this ambient temperature, so that the pressurization is fast. So for faster pressurization of the container, this external gas pressurization is preferred. And pump transfer is preferred when there is large quantity of cryogen has to be drained in short period of time, especially for large flow rates. And this pump is connected to the inner vessel, or where the cryogen is stored, so that once you start pump, it will give you the liquid where you want to fill with some pressure. Okay, so these are the different types, three major types for draining the system, the cryogenic vessel. And then apart from that, we have to see the safety devices, because safety is another important parameter for designing these storage vessels. And there are various safety instruments which is being, or which need to be provided in these cryogenic containers. The first one is the inner pressure relief valve, because when cryogen is stored, it will build up the pressure slowly because of the evaporation, and that pressure has to be relieved intermittently, so that to keep the inner vessel in safe operating condition and less than then. So these are all, these two shows the pressure relief valve, whereas this is a manual valve for draining event manually, draining the vapor manually, and this is a this is the safety valve. This is a spring loaded safety valve, And when the gas pressure is more than 10% of the design pressure, this pressure safety or this spring load is adjusted such that when the pressure is more than 10% of the design pressure, that opens up and all the gas is relieved through this. And once the pressure comes down, then the safety, this relief will, the spring load will sit down back, and there this inner vessel is in safe condition. And also you are having provided all the containers are provided with bursting disc. This bursting disc is a redundant safety. Suppose this safety valve is not working, or when the pressure inside the container is 10% more than the design or operating pressure, then if the safety valve is not relieving the pressure, high pressure what is there inside the inner vessel, that time this bursting disc will open up if the pressure exceed by 10% of the relief valve. That means when the relief valve is not working and the pressure inside the container is now 20% more than the design pressure, that time this bursting disc, the disc will burst. It is designed so that with that pressure, there is a conical cone-like structure and the film which can withstand the atmospheric pressure. If the pressure is more than that, then this cone pierces to this film so that all these vapors escapes to that. And again, apart from that, pressure relief valve and bursting disc, one has to provide the annular space bursting disc assembly. This is generally provided with the outer vessel of the cryo vessel, and this protects the outer from excessive internal pressure. If there is some leak from the inner vessel to this vacuum space or to the insulation space, then the pressure will build up, and that time this both the containers should be saved. And so this interspace is provided with the bursting disc. The outer vessel is provided with another burst disc assembly, and that helps to preventing the collapse of the inner vessel due to the excessive internal pressure. If also some pressure is coming, excessive internal pressure collapsing of the inner vessel and also the outer vessel. So that time you have the ruptured disc which is having a set value of within 35 kilopascal to 50 kilopascal, that is of the order of 0.35 bar to 0.5 bar. If the pressure in the interspace is around that value, as per the set value, then the bursting disc opens up, and that time burst literally, and that time this both the containers are safeguarded. And this pressure building generally happens if there is a leak developed in the inner or outer vessel. So that way, that time this pressure will build up, and with this bursting disc, both the inner and outer vessels are protected. Okay, so that is the total design part of this safety, including safety for this cryo containers or cryo vessels. Also, as I told, insulation also plays an important role for all these cryo containers, and there are different type of insulations available which can be implemented to these cryo vessels. But as I told, there are different types of insulations like expanded foam, then gas-filled powders and fibrous materials. Vacuum alone can be used. Then this gas-filled powders, evacuated powders, and fibrous materials. Over these, if we evacuate, then also the heat transfer is minimized. And then opacified powders, when you add some opacifiers to this powder and fibrous material, that is another opacified powders. And multi-layer insulation, that is the ultimate insulation, the super insulation. But specific insulation to be used for a particular application is determined through the compromise between the cost, because when you go for installations like multi-layer insulation, it costs more compared to all other insulation. Or if you vacuum, also you need some special arrangement and vacuum pumps, all that. So you have to compromise between the cost and its application, and weight, ruggedness, all is into consideration. Okay, so in addition to the effectiveness of the insulation, all these other parameters also has to be considered. And let us see quickly different type of insulations. First is the expanded foam insulations. These foams have cellular structure, as you most of you have seen. Different type of foam sheets or foam tubes, and also this is foam insulation with vapor barrier. That is a little advantage. I'll come to that. And polyurethane foam, polystyrene foam, rubber, silica, and glass foam all comes under foam insulation, and generally when they are making this expansion of, or this making this foam insulations, they use carbon dioxide. And the disadvantage of all these insulation or foam insulation is that it has large thermal contraction, and if the foam is fixed to the vessel or to the transport line, then the foam would crack during the cool down because of very cold fluid passing through that or getting stored in the storage vessel. So it sinkages and then cracks occurs. And once cracks occurs, then water vapor and air flows through the cracks and reduces the insulation. So this is generally used um, for short duration time instead of having bare line. You can put this, and it is not that effective, but easily you can put to any structure or set. And as I was telling, when the air flows through it, then the thermal conductivity of the insulation increases. So to prevent this airflow or the water moisture to this foam, you are provided with the vapor barriers. That way it reduces the heat transfer. Then next type of insulation is the gas-filled powders and fibrous insulation. So this fiberglass, powdered cot, or perlite, santocell, rock wool, and vermiculite comes under this type of insulation. And the reduction or the elimination of convection due to small size to void within the material when we're packing. So that time some voids will be there, and that time it eliminates the convection transport, because of which again the performance is improved compared to foam insulation. And for very fine powders, the distance between the particles may become smaller than the mean filter of the gas within the insulation. And that time, this gaseous conduction shift from continuum to free molecular conduction, thereby reducing the heat transfer, and thereby it reduces the heat transfer because the thermal conductivity reduces. But this disadvantage of this type of insulation is that the moisture and air can diffuse to the cold surfaces, and again it will create more heat transfer and effectiveness reduces. Then the next type of insulation is the vacuum insulation, and this is extensively used in small laboratory-sized viewers. And that reduces it eliminates the solid conduction and gaseous conduction, and the only mode of heat transfer in vacuum insulation is the radiation and the gaseous conduction of the residual gases. Still some part of gas will be there when you evacuate it. Still some part of gas will be there, and through that also some gaseous conduction takes place. And this the rate of radiant heat transfer is given by this equation, considering all this emissivity factor and the configuration factor, and sigma is the Stefan Boltzmann constant, A1 is the area of the surface 1, and this is the T to the power 4 minus 10. This is the temperature difference of the warm temperature to the temperature. And the radiant heat transfer can be reduced by introducing the floating radiation shield of highly reflective materials between the hot and the cold surfaces. And when these radiation shields or floating radiation shields comes into play in vacuum insulation, that is known as the super insulation. We'll discuss in the next slide. Next slide. So this is the another what I was telling, that the powder and fibrous insulation. But if you pump over that, then this in this type of heat transfer in the powder is gaseous conduction is the primary mode of heat transfer in powder and fibrous material. So the method to reduce this gaseous conduction is to evacuate this space between the powders or fibrous insulation material. And this curve shows the variation of thermal conductivity of typical powder insulation. So it shows that when from atmospheric pressure to almost 15 torr, this is the torr is given in this column. And when you evacuate up to 15 torr, that time there is little change in thermal conductivity of this powder insulation. But from 15 torr, from 2 kilopascal to again evacuate to the order of 7.5 into 10 power minus 2 range, then the thermal conductivity is immediately proportional to the gas pressure, and at that time the thermal conductivity reduces drastically. And below 1 pascal, or that is 7.5 into 10 power minus 5 minus 2, the magnitude of gaseous conduction heat transfer is much smaller compared to the heat transfer by the radiation and the solid conduction, and that times thermal conductivity stabilizes. And this type of evacuated powder and fibrous insulation is very effective for storing bulk quantity of liquid nitrogen, liquid air, liquid oxygen, or liquid argon. And when you add some opacifiers, this is opacified powder insulation. As the name suggests, when you add some opacifiers like copper or aluminum flakes to the evacuated powder, that is known as opacified powders, and in that way the radiant heat transfer is further reduced. So using the optimum number of opacifier in this powder insulation, the thermal conductivity can be reduced to almost 5 times. And here this graph shows two such opacifiers in the powder insulation. One is the copper centrocell and the second one the aluminum centrocell. And you can see that this is the percentage weight of opacifier in the powder insulation, and you can see that the thermal conductivity reduces drastically when you add opacifiers of optimum percentage, optimum weight. But okay, so because of that, this performance of this insulation improves more compared to evacuated powder insulation or the powder insulation only. And this is very useful for large capacity stationary storage viewers. But their disadvantage is due to packing, due to vibration. If vibration occurs, like your transportation vehicles, then it is not that useful, because the opacifiers will try to settle at the bottom, and then thermal short circuit may take place, thermal shorts may develop, again increasing the thermal conductivity. So one has to see that this opacifier should not get thermal short, and then it is useful for bulk storage of these solvents. The next type of multi-layer insulation is the vacuum insulation with milers, where you use alternate layers of highly reflecting materials in this vacuum zone. Generally, aluminum foil, copper foil, or aluminum mylar, and with low thermal conductivity spacers like fiberglass, paper, glass fabric, and nylon net, as you can see in this figure, is put. This is the one layer aluminum foil, then separated by a spacer, and it can be of different materials like fiberglass, paper, that. And then you put, and also there also matters the optimum number of insulation, the layer of insulation, and the packing density of this material insulations or the milers. And because of that, when you are putting this in the vacuum space, that time your thermal conductivity reduces very effectively. And then you can see here when we are putting this multi-layer insulation, and when the gas pressure on the evacuation is going on, and at gas pressure of around 1.3 into 10 to minus 4 pascal, the thermal conductivity is very, very less. So thermal conductivity reduces of this insulation, and then you can see that the evaporation rate of heat transfer to the inner vessel is very minimal. And instead of putting this pressure in between this mylar or aluminum milers, one can use crinkling or embossing with sheets, so that they only touch at a few discrete points, and that time no special is required. Then it has to be effective when this vacuum pressure is at least order of 10 to minus 4 millibar, and then with radiation shields it performs better, and in that way, all modes of heat transfer takes place. All modes of heat transfer is reduced to the minimum. So this is the best insulation for any cryogenic application. So after the consideration of all these design parameters for storage vessel, let us go quickly to the cryogenic transfer lines. I'll be little picking up so that we try to finish the list. So there are different type of transport lines, rigid transfer lines, flexible transfer lines, and again that is based on the configuration and based on the insulation. Again, uninsulated lines, and then insulated lines made up of fiberglass, polystyrene foam, polyurethane foam, then foams and fibrous insulations as in cryogenic storage vessels. Then the vacuum or super insulation super insulated transfer lines. So this shows the cross-section view of the first picture, shows the cross-section view of a rigid transfer line, and you can see this is the inner tube through which this cryogen is transferred from the storage there to the end application. And also here we have to see that all type of heat transfer should be minimized so that the cryogen can easily pass on from the storage there to the end application. And this is the outer vessel, which is also again connected with the bellows to take care of the thermal contraction. Then this is the interspace between the inner tube and the outer tube with the vacuum jacket. And you have different type of spacers to support the inner tube in the outer tube. And this is of course the vacuum port to evacuate all these residual gases between the interspace. You can see that this type of transfer lines for effective use of these transfer lines, one uses the banner type, where this vacuum is extended and till the other part get connected. This is another tube of similar with a male part, and with a female part again it will come, and here the flange will be tightened at room temperature with O-ring seal. And because there is a vacuum extent to some extent to the other pipe, so the heat transfer from the ambient is directly not going to the inner tube, and that way we are reducing the heat transfer from the outer tube to the inner tube. And this Bernard joint we'll discuss in another slide, where how it looks like, and you can just easily visualize that. And this is the photo of a rigid transfer line which we have developed. I was involved in developing this in our center, and this is to connect our liquefied this liquid nitrogen plant header, where this nitrogen gas gets liquefied, and again it has to come and collect in the DUR of 500 liters capacity. And you can see this also is a vacuum insulated super insulated transfer line with a vacuum extent, which is the inner tube which goes to the vacuum pad. Though the vessel is connected at this plans, this K50 plans, but still you can see the vacuum extent here, so that minimum transport takes place from the outside to the inner tube where it is carrying the kerosene. And this was the cross section as well as the photo of a flexible transfer line. So here both the lines are flexible in nature, inner as well as the outer one, flexible bellows, so that for better maneuverability and there is space constraint, that and this type of flexible transfer lines are very useful. And this is the cross section view, and this is the photo of a commercial flexible transfer line. Okay. So depending on the insulation, they are again classified as uninsulated lines or porous insulated type or vacuum insulated type. So most common uninsulated type is most economical for a short length and a short duration of cryogen flow, and it is suitable for liquid air or liquid nitrogen flow. And when for short period and short distance you are transferring this cryogens from the storage, initially when the cryogen start flowing through this transfer line, first formation will occur because atmospheric air contains moisture, and that will get crusted on the surface, and that also acts as a additional insulation, and that way the heat transfer subsequently reduces. Suppose example, for a bare line, when there is no insulation or there is no cross permission, for liquid air passing through that, it gives 1.8 kilowatt per meter square. That is the heat input from the outside ambient, from the ambient to the transfer line or to the fluid. Then when this first formation occurs of 2.5 meter frost when it has happened, that time this heat transfer also minimized. So to 1.8 to means it reduces from 1.8 kilowatt per meter square to square meter to 1.1 kilowatt per square meter. So and but it is not suitable for liquid helium application or liquid helium application, as the condensation of vapor, condensation of air over a pipe leads to high conducting losses. Also, when you are using for hydrogen application, one has to see that the oxygen concentration when air occupies over that, it is also not good. It is sometimes like disaster. Okay, so then porous insulation types improves the, it is a improved version compared to uninsulated one, and that improves the insulation compared to this. And here you can use different type of insulations like fiberglass, polystyrene, or polyurethane foam. And for that, the vapor barrier is required to avoid the diffusion. I was telling in previous slides, so that the diffusion of moisture into the foam should not occur. And the other type is the vacuum insulated line. This is especially used, transport line used for long distance and for long duration time. And here, similarly, it consists of inline, the concentric vacuum jacket, and with multi-layer insulations, or vacuum balloon sometimes is used. This thermal contraction is avoided for long pipes, long transport lines, by providing the U bends in the inner pipe, and the spacers of generally used. Spacers are used to support the inner tube in the outer tube, so that it is positioned properly without any sagging or accumulating the cryogen flowing to that. And the spacer should have low thermal conductivity and should have a high strength to take the load, and a low outgassing rate, so that it should not deteriorate the vacuum or the performance of the insulation from the in the interspace, so that more heat transfer, if it deteriorates, then more heat transfer takes place from the outer pipe to the inner pipe. So one has to take into consideration all this low heat outgassing and then low specific heat. And generally, the spacer materials are selected as plexiglass or fiber-transposed plastics or fluorocarbon plastics. Sometimes also bakelite used for these applications. And there should be, while designing this spacers, it should have low thermal contact. Low thermal contact, or the point of contact from the spacer to the inner and outer surface, outer tube should be minimal. Okay, so different type of design like triangular and rectangular spacer, so that only at point contact to the outer vessel, so that minimal heat transfer takes place. And should not block the annular space. That is also another consideration. So this annular space, after the performance periods are for making proper evacuation, you need that annular space to be properly approached to the vacuum port, so that whatever residual gas is there between the inner and the outer pipe has to be removed. So that should not block the annular space. And sometimes also roller spacers are used to avoid the contact stresses whenever needed. This type of arrangement is used as for spacer designs. Then the banner joint, this is the joint, it's a high performance cryogenic pipe joint, and used where low heat inlets occurred, and these are generally frequently you have to disassemble the lines, long lines, for some when that needs this lines should be separated. Then this type of joints are very efficient for cryogenic application. And you can see here, this is one pipe which gets connected and extend to the other pipe, and the vacuum is extended here, and the fluid which is passing through the inner tube. It ends the this is the end of the first tube, and whereas the second tube starts from here. And if at all some this gap is so maintained that if the cryogen is coming here, it will make the vapor seal and because the sealing is at room temperature. And V-band clamps, then this interface is evacuated so that insulation is maintained for the first line here and for the second line here. And when joining, you see between the two pipe joints, that is also evacuated. So it is a continuous, like a continuous evacuation or a continuous vacuum for both the lines. So this is especially used for the lines which are seldom, very rarely open. Okay, so this is the consideration for all these transport lines. So let me give some idea about the development and the studies on super insulated transport lines what we have done in our laboratory. And so our practical actual aim was to develop a 3-meter, 5-meter long flexible transport line for practical applications. So towards that, initially we developed a 3-meter long flexible transport line for quick disassemble type, so that it can be easily disassembled as many times you want, and can perform or can vary different experimental conditions to study, suppose the effect of insulation or the effect of the distance of the spacer material. Special optimization of the special distance. For that, different type of studies, we have first made a quick disassemble type flexible transport line, and this shows the details of this flexible transport line of 3-meter long. This is show the inner pipe where the end part, and whereas you can see the inner part is the flexible bellow, and the outer also is flexible bellow. And liquid cryogen is carried from here. You are having F25 for evacuation portion, and you are having a vacuum till you connect to the another line. Okay, so here you have that flanges to join one line to the other, and this shows the photographic view of this end. So here we are having we have made some arrangement with the nuts, brass nuts, so that it can be easily dismantled. And this is the other end. This is having some feed through to measure the temperature profile or the cool down studies, all that. And also you are having gator here to observe if any gas is getting cold or because of degassing of the material or the insulation. And then the other end with this is for feed through, other end which for vacuum insulation for evacuating the line. And the next slide show you the actual photographic view of the line which I have developed. This is actually feed through what I was telling, and this is the vacuum port. This is a spare part study, and you can see that if I open my one end, then everything comes out through the other end. And this is the part which completely comes out, detaching from here. It can completely comes out, and you can see in between we are having a mylar insulation, this mylar with some spacers, and then this is the spacers, and we have done the optimization of the spatial distance study, because this also gives the spacer wherever it is connecting from the inner tube to the inner bellow to the outer bellow. Some part of heat transport takes place from the outer bellow to the inner bellow. So this should have minimum number, but at the same time the inner bellow should not sag to the outer bellow. So that studies we have also done, and this is the total view and this is the inner bellow, and this is the total assembly of the 3-meter long transport line. And this transport line is of 20 mm ID, inner tube ID, inner bellow ID is 20 mm, and inner bellow OD is at 26.8 mm, whereas the outflow is inner ID is 51 mm and the other one is 70 mm, and this shows all air connection details, which I won't go to that. But some design parameters which we have to consider now for designing these transfer lines. First is the inner tube diameter, and this inner tube diameter is the diameter needed so that for a particular flow rate, you should your diameter of the tube should be sufficient so that it should not give any backflow or impedance, pressure drop, or impedance that. So based on the quantity of cryogen has to flow for many liters per second, we have to calculate the diameter, minimum diameter of the tube, and that is given by this equation K1 multiplied by m dot, that is the mass flow rate. Here it is given in liters per minute, so kg per minute. So per second it is divided by 60, and then this is come to grams per second grams, and then to get the diameter in millimeter multiplied by 10 × 3. So from this equation, one can find out the minimum diameter of the tube needed for a particular flow rate, and then after fixing the diameter for a particular flow rate, one has to calculate the thickness of the inner shell. That is given by the equation An is the factor of safety into internal pressure, because the inner tube, then outer diameter of the inner tube divided by 2 into allowable stress plus 0.8 into internal pressure. And similarly with this, we can find out the thickness of the inner bellow, and the thickness of the outer shell is designed from this again considering the critical or the collapsing pressure, and it is same as 2E multiplied by d by t to the power q 1 minus mu square, and where mu is the Poisson's ratio. And then also pressure drop, one has to find out for the transfer lines, and this is for single phase flow, assuming that the fluid what is going is 100% liquid, and there is no void or there is no vapor. So for that single phase flow, this is the equation for single phase flow, that is delta P by delta L over unit length. So the pressure for unit length, pressure drop in unit length for single phase flow is given by F into m dot square and multiplied by 1 by 2 GC rho dN, where GC is the conversion factor, and A equal to pi rho d square, that is the inner diameter of the tube where this cryogen flows, and rho is the density, and E is the cross-sectional area. Similarly, the pressure drop for two-phase flow is given by the Lockhart-McNeil equation correlation, and this is the equation delta P by delta L for two-phase flow is given by pi multiplied by delta P by delta L over the total length. Okay, so so where pi is the Lockhart-McNeil parameter, and that can be calculated from this equation, so what is given here. And the pressure drop in flexible transfer line also is given by slightly modified equation. That's delta P by number of corrugation, because corrugations are there for below bellows. So that is given by this equation for pressure drop for single phase flow. And for corrugation, it is given lambda into 1 by d1 n into tau, that is and rho is square by 2, where v is the velocity and lambda is the coefficient of friction, that is 1.6 for zero bending radius, and tau is the resistance coefficient, and for Reynolds number between 10 to the 4 to the 10 to the 5, the value of this resistance coefficient is 0.0625, and if the Reynolds number is greater than 10 to the 5, then this resistance coefficient is taken as 0.0. So from this equation, we can find out the pressure drop for single phase flow in flexible transfer line, and also the pressure drop in two phase flow is considered from that equation. And if you calculate or if you go solve it, you will find out the same equation. This is what is given for the single phase flow. Okay, that is for number of corrugations. But here you have to, for two-phase flow, you have to consider that vapor fraction and all that, vapor and liquid. So all these data, what is C, the constant that can be taken, CL, CV, all that can be taken from this table, and one can find out the pressure drop in flexible transfer line, both for single phase as well as for two-phase flow. And then after considering the calculating the pressure drop, one has to calculate the heat load on this transfer line. So this is the equation what I was showing you earlier. The same way it is if it is only for vacuum. This was given for vacuum insulation, and this radiant heat transfer is given by this equation. If P into 1 F 1 to 2, then sigma A1 T2 to the power 4 minus 2 and 4, where AP is given by this equation 1 by AP equal to 1 by E1, that is the emissivity of the material, and plus A1 by A2 into 1 by E2 minus 1. And if it is vacuum plus Mylar, then this Mylar, this 1 by AP takes to this equation, and where this number of layers comes into picture. Then for free molecular heat conduction, if the path, free molecular path is greater than the distance between the inner and the outer vessel, then the heat load on the inner tube is the free molecular conduction, and that is given by QG dot, is given by G into P into A1 T2 minus T1, where G is given by gamma plus 1 by gamma plus 1, and GC into R by 8 pi T2 per half into FA, and FA is given by this equation. So from this equation, one can find out the free molecular heat conduction, and then the heat load at the ends, where the metallic conduction takes place at the joints, where there is no vacuum. So that time, where it is planar joint or at the ends, this is given by that metallic conduction equation is given by this Q m dot, that is the metallic conduction heat transfer rate, is equal to 2 pi L into theta 2 minus theta 1 by ln R2 by R1, where theta is the thermal conductivity integral, that is the integral of K, that is the for liquid helium application, and T is the temperature, outside temperature, and K dt. From that, one can find out the total load due to metallic conduction, total heat load due to metallic conduction. And from this equation, what is given, one can find out the time taken to cool down the transfer line. This equation is time taken to attain the steady state is given by summation of this m dot total mass of the transfer line that need to be cooled. This is the mean specific heat for the material, and then T0 minus TSS room temperature minus steady state temperature of the liquid temperature, what is going, minus B, that is the total number of inner line, volume of the inner line, and rho SS, that is the density of the fluid at the final stage into the steady state, multiplied by USS, that is the internal energy of steady state, minus HF1, which is the enthalpy of the saturated liquid at the inlet condition, minus rho G0. Rho G0 is the density of the gas initially in the line, and then U0 minus HF by mg2, that is the mean gas flow rate exit at the exit, multiplied by a mean exit enthalpy temperature of the fluid minus the enthalpy at the inlet, minus this mg multiplied by exit2 bar minus hf1, then minus 0.5 QSS, where the QSS is the heat in leak from the ambient. Okay, so from that one can find out the time needed to cool down the transfer line from ambient to the operating condition or the steady state condition, or the temperature of the inlet fluid. And also the mass of liquid can be mass of liquid required to cool down can be found out from this equation. As I have not much time, I'll just go a little faster. So these are the equations which are given for finding out the specific mass required to fill the line with liquid. Then a specific mass evaporated by ambient heat transfer during cool down. From this question one can find out. And this, of course, I told the mass required to cool down the line. Then to calculate these are the equations which we are now having for measuring, for estimating the pressure and the heat load calculations. Then we have developed a MATLAB code to find the pressure drop in single phase as well as in two-phase conditions. Also to calculate the heat load to the inner bellow of the fluid from this outer bellow. So then I'll just quickly go through that. This is for liquid helium flow. This is for single phase flow. We have taken two different conditions. One is for 15 liters per minute and the other one is for 20 liters per minute. And you can see that for low flow rate, and this is against the pipe diameter. And when the pipe diameter is reducing, then the pressure drop also is increasing. And for 15 liters per minute, it is around 26, 27 pascal per meter. Whereas for 20 liter, when the flow rate is little more, that pressure drop also is increasing to almost 43 pascal per meter. Similarly, for two-phase flow, when two-phase flow means some quantity of vapor is there in the liquid. So for different vapor fraction, that is for 10% vapor in the liquid, and then 20%, then 30%, and 40%. We have taken 4 criteria and calculated the two-phase flow pressure drop per meter of the pipe bellow. And then we saw that for less void fraction, that is for 10% void fraction, your pressure drop is around 80 pascal per meter. And for when the vapor fraction or the void fraction or the quality of the fluid is less, then that time your this pressure drop in two-phase condition increases to around 180 pascal per meter. Similarly, for 20 liters of liquid helium flow, and if the diameter is increasing, then at this around 26 millimeter of tube diameter, the pressure drop for 10% void fraction is around 130 pascal per meter, and it increases with the increase in void fraction. Of the liquid of the inlet condition. Then also we have calculated the pressure drop for liquid nitrogen flow, and this is shows this is little higher compared to liquid helium and liquid helium flow. And for single phase flow, it is around 110 pascal per meter, and for 20 liters per meter, 20 liters per minute, it has come around 200 pascal per meter. And similarly, for this different percentage of void fraction, this has increased. For 10% void fraction, it has gone to 3,000 pascal per meter, around 3,000 pascal per meter, to almost 8,500 pascal per meter. That means when the void fraction is more, then you are having more pressure drop. Okay. Similarly, for 20 liters per minute, this has again increased from this compared to 15 liters per minute. Excuse me. Yeah. So then we have also calculated the heat load to the 3-meter flexible transfer line. You can see here, this is the radiation heat transfer, and this is the total heat load, and this is the free molecular conduction, and combine these two will get the total heat load. And This is when also it's for 0.01 Pascal vacuum. This shows that when the tube diameter is increasing, that time also your heat load is increasing, with the reduced diameter, the heat load is minimizing. So one has to optimize the diameter of the tube, and this is the value what I got for 26 mm diameter tube value. Okay, and this is for uh, 30 is 20 liters per minute of flow, and it has a slightly this is for liquid helium flow, and this is for liquid nitrogen flow. And you can see that compared to liquid nitrogen flow, this for liquid helium flow, this heat load is a little more, because uh, the temperature gradient from the ambient to the transfer line where the cryogen or the helium is going is more compared to when LN2 is present. And this shows the comparison of the MATLAB results with some experimental results. This is already published in literature, and we have compared how good is our data when we are doing the MATLAB analysis. Then you can see that this is the heat load through the radiation for liquid helium and liquid nitrogen. We have taken the data, and for liquid nitrogen, it was 0.1507 for radiation heat transfer, and also the premolecular conduction is 0.37. When you combine these two, it comes around 0.5244 watt per meter, and this is the published data, which is 0.54 per meter length of the transfer line with a Banach length of 0.7 meter. So we have maintained the same condition, and our values shows nearly equal to the published data, indicating that the calculations what we have done through MATLAB is quite good and matches well to the published data. So because of that, all other data, if you see like a heat load through the conduction for liquid nitrogen, because for liquid helium we don't have data, published data available. So we are comparing with the liquid nitrogen flow published data. And this is the heat load through conduction, 7.6 watt in total for 1 meter length, and 7.8. So it is nearly matching to the published data, and the heat load, total heat load for our case is 8.23, and say it is around 8.34 in published data, and the mass required is a 0.2 feed line is 0.875 kg, whereas the published data is 0.95 kg. So all our data are matching well to the published data, indicating that whatever calculations are done, I think for pressure drop and heat load, pressure drop that also holds good. And this is the comparison for heat load. And to test our line, we have developed an experiment system to study on this flexible transfer line. This shows the experiment system where we are having a supply container for supplying the cryogen through the transfer line, which is here. We are having some temperature sensors to measure the temperature at different time duration of the flow, starting from the initial condition to the steady state condition, and then here the receiver container, we supply the cryogen and pass through the transfer line and collect to the receiver viewer. And the quantity of liquid supplied and the quantity of liquid received in the receiver container is weighed by this electronic weighing balances and recorded in the computer. So in this way, we study the temperature, the cool down of the line, the warm of the line. So this shows the typical cool down curve for the transfer line, 3 meter long transfer line. And you can see that we have put different sensors, as is told, starting from the inlet. It is sensor A is at 0.5 meter from the inlet, B is 0.5, 1.0 from the inlet. And so at every 5 meter, 5 millimeter, 500 millimeter distance, we have put the sensors, and you can see that the sensor at the middle, which is at 1.5 meter from the inlet, is at the place of the transfer line is cooling fast compared to other places, because the ends which are exposed to atmosphere, that is the sensor at 0.5 meter from the inlet, or the sensor which is 5 meter, 0.5 meter away from the discharge end, that is the sensor E, that is at a higher temperature compared to other, and so the sensor C at the middle of the transfer line, and that place gets cooled down because the heat transfer is minimal. Similarly, this shows the warm-up line, and here you can see this is the coldest part when we are cooling down, and there it takes some time to start the warming. Relatively, it is reciprocating that this is the at 0.5 meter away from the inlet, and this 0.5 meter away from the outlet. So, and all other follows the same pattern. And here, of course, depending on this heat input to the sensor, the point where the sensor is located, you get this type of profile. And this is for bakelite spacers at a distance of 150 millimeter with vacuum insulation, vacuum of the order of 4.3 to 10 to minus 5 millibar, the 20 layers of MLI. And this table shows the effect of insulation on transfer line for 20 liters of liquid nitrogen transport, that is the amount of liquid collected in this reservoir. So then you see that these are the different experimental conditions. In bare tube, we are passing 90 liter, then 40 liters gets evaporated without any insulation. And when it is having vacuum with the 28 number of bakelite spacers, this quantity of evaporation, the quantity of evaporation was 40 liters without any insulation, now has come down to around 80 liters, and same also is holds good for nylon ropes. This is another type of spacer which you have put these nylon ropes as a helix to support the inner and bellow within the outer bellow. That time also is almost same compared to the vacuum insulation. And this shows the cool down curve for different layer of multi-layer insulation. We have done experiments with different layer, like starting from 6 layer, 10 layer, 15 layer, and 20 layer. You can see that the 6 layer is at a high temperature and it's cooling down, taking place much more time. Similarly, the one at the end, when the number of insulations increases from 6 to 10, then the cool down time also reduces, indicating that there is a less amount of heat transfer is taking place from the outer bellow to the inner bellow. And you can see at 20 layers of multi-layer insulation, this curve, which is blue in color, that is going past and come to the lowest temperature, and compared to all other sensors, and it takes relatively less time compared to all other layers. Okay, so we have optimized 20 layers of MLI for our practical applications, because if you go for 26, and there is not much improvement, but you will have more thermal mass. Okay, that also in turn will add on to the thermal mass, so the cool down time also is slightly more compared to the 20 layers of multi-layer insulation. So we have 10 bakelite, and for different milers, what I told that the cool down curve what is showing for different layers of multi-layer insulation, you can see the effect of multi-layer insulation on this transfer line. And with vacuum of same order 4.3 into minus 5 millibar, and keeping the bakelite spacers at 28 in number, by varying the multi-layer insulation, you can see with 6 layers of MLI, the quantity of coolant to evaporated is 16.5 liters, and for 10 layers, it has come down from 13.82 from 16.5 liters, and 15 layers of MLI with all other parameters constant, from it has come down to 10.44 liters, and with 20 layers of MLI, it has again come down to 8.25, whereas for 26 layers, it has come to 7.01 liters, while transferring 90 liters of liquid nitrogen. So with that, we have fixed to 20 number of MLI. Then we have done the spacer optimization, because the number of spacers we are putting, more heat transfer also will take place at the contact points of the spacer to the inner bellow. So keeping this 20 layers fixed, we have now optimized the spacers. The told spacers are used to support the inner bellow within the outer bellow, and the spacers should have a high mechanical strength, less thermal contraction, and less thermal conductivity, and it should be easily machinable. So we have selected Hilum spacers here, that is the Bakelite in the name, and the trend name is Hilum. So, and this is the spacer design, the ID of the outer bellow, and this is the OD of the outer bellow, and you are having the spacer in between. And we are having some holes where this feed through for the sensors is going through, and this is again dismantled type in two halves, and then after putting it is just clamped over the inner flexible bellow. And we have made it from Bakelite, because the thermal conductivity is also low, and also it is easily machinable. And we have taken this shape because we are designing the flexible transfer line. So very sharp points like triangular or rectangular spacers may create damage to this internal or this inner and outer bellows. So inner to the outer bellow. So, and also if the thickness is less, it can also go into the planks. Okay, so because of that, we have designed some Hilum spacers with some thickness of around 10 mm, so that it sits properly in the interface, supporting both the inner bellow to the outer bellow. And then we have done studies with 20 layers of MLI and different number of Bakelite spacers with vacuum of 4.3 minus 5 millibar. And you can see with the 20 Bakelite spacers, the quantity of filling to evaporated with 20 layers of MLI is 8.25, and for 19 it has come down to 6.56 liters, and for 14 Bakelite it is for 14 spacers it is 5.18, and for 11 it is 4.70 liters. And when the Bakelite number or the number of spacers is coming down, that time this quantity of liquid evaporating is less, but when this number is very less, that time the sagging of the bellow is occurring and a lot of liquid accumulation occurring. That is again is another problem. So that should not happen. So towards that, we have optimized the number of spacers to 14, and we have done the calculation, heat load calculation, and that is the effect of spacer distance. This graph shows the effect of spacer distance on the total heat load to the transfer line. You can easily see here that when the number of spacers is less, the total heat load is less. But when the number of spacers is increasing, the total heat load through these spacers is more. And so one has to optimize the spacer distance, and we have optimized this spacer distance at 200, which corresponds around 16 number of spacers for this 3 meter long transfer line. Then after doing all the studies, then the next thing was our actual development for a 5 meter long flexible transfer line, and this we have designed for the practical application with Baynard type ends. This shows the schematic of this 5 meter long flexible transfer line. This is the flexible transfer line of 5 meter long, where there is inner bellow supported by the outer bellow, and here is the Baynard end of again 500 meter length with vacuum extent from this plants, K50 plants, to the main diva, where it has to transfer this. And this is designed for liquid helium application, and liquid helium has to come to the user to fill the small divas or practical applications. And here also again you can see this is the clamp end where it has to be connected to the storage diva from the main storage diva to the user's diva. That time also this vacuum extent is again 550 millimeter. And this shows the details of this detail dimension of this 5 meter long flexible transfer line. So here you can see the bare and the inner tube is a 21.3 OD, and this is 42.3 for this vacuum jacket. And this is the K50 of having diameter of this quick disconnect flange that is 70 dia. And you can see the below inner below ID is around 34 and OD is 34.5 whereas the outer below ID is around 85.38 and 100 in OD. And over this again we have used this 1 braided flexible braidings. So the total diameter of this 5 meter long flexible line comes as around 102 Okay. And this shows the photograph of the 5 meter long flexible transfer line. You can see whatever is telling is the point, the banner extension where it is connected to the DVAR for transferring liquid, and this is the end where to collect the liquid. And we have done studies for LN to liquid nitrogen flow, and it is working fine for nitrogen, and it will be very useful for liquid helium application also. And this shows the cool down and warm up curve for 5 meter long flexible transfer line. And this shows the 3 sensors which are 0.5 meter away from the inlet, and the other one is 0.45 meter away from the inlet, that is 0.5 meter from the exit end. And this is the middle sensor located at 2.5 meter from the inlet. And here you can see that for this 5 meter long transfer line, it takes for nitrogen application, it takes around 50-60 seconds to pull up to the operating condition of the liquid temperature. And this is the warm up curve. You can see the middle sensor, though the other two ends running very fast. The middle sensor, which is the coldest point of this transfer line, it takes around 650 seconds to start the warm up. And after this, you want to conclude like that cryogenic fluids are used for large number of applications, and cryogenic fluids have a low boiling point at ambient pressure and very low latent vaporization, and also high liquid to vaporization ratio. So that demands for special storage and transport systems for storing or transferring these cryogens, and portable and large size storage and transport vessels with different type of installations are available, but most of them are vacuum or super type for particular applications, and rigid and flexible transport lines for transferring the cryogenic fluids. Then the variety of installations that can be used for both storage and transport systems are the vacuum insulation with multi-layers, that is MLIs, multi-layer installations. That is known as super insulation, is the most effective insulation for cryogenic fluids. And studies show that with the optimization of the mylar layer and the optimization of distances, the boil off of the cryogenic fluids can be minimized during the transport or storage during the transport process. During the transport process. So also studies are in progress to improve the performance of the storage and transport system of these cryogenic fluids. So because the nature of these cryogenic fluids, one has to take special consideration for storage and transfer of these fluids. With this, I thank all of you for your kind attention and patience for listening, and it's quite late, some late from everyone's time. Thank you.
Thank you, sir.
If you have any questions, yeah.
So we have a question, sir.
Yeah.
So it is from Kiran Kumar Rogde, one of the participants. He's asking,
okay,
what is sloshing excitement effect during cryofluid transportation, and how we can control the same?
Yeah, splashing, right?
Yes, sir. Yes, sir.
Yeah. So when you transport these cryogenic fluids, because there is a large temperature gradient, because the cryogenic fluid, for example, you take liquid nitrogen that is at 77 Kelvin, and you are transferring suppose to a viewer which is at room temperature of 300K. And when this liquid suddenly goes to this from 77K to a 77 Kelvin to 300 Kelvin surface, immediately it will try to boil up very fast, and because of that, this liquid will just try to bounce back, and or it won't evaporate properly, and whatever is getting evaporated with that vapor, the liquid part also will try to come out from the container instead of storing in the container. So one has to take care of that. The taking care of that is initially you can transfer with a low rate of flow, so that the container, the receiver container, slowly gets cooled down instead of high quantity getting splashed out. And once it comes to some reasonable temperature, lower temperature, then slowly you can increase the flow rate, and by the time the content also will sequentially get cooled down further and further, and the collection will be better. So that is one way of doing this. And also when you are handling the cryogens, suppose it gets spilled suddenly and the person is not aware of that, and sometimes it goes to the shoes or your trousers. So one has to go through proper safety instructions for handling cryogenic fluids. So these are the two parameters I think one has to understand: the cryogenic, the nature of the cryogenic fluid, and the safety to handle all the cryogenic fluids.
Okay. So there's one more question asking like how the pressure and
Yeah.
temperature maintained during the transportation of cryofluids.
Okay, so during the transportation of cryofluids, as you know that for first let us come to the pressure, augmenting the pressure, because I told you that all these cryogenic containers are fitted with the safety devices. Okay, there is a pressure relief valve, and if the pressure is exceeding more than that set value, then this pressure relief valve will open, and the extra pressure will go out through this relief valve, and once it comes to the normal operating pressure of the internal the inner vessel, then the safety valve closes and it maintains the temperature, pressure. So that is the way how the pressure is maintained in the container, okay, in transportation vehicle. And as long as the temperature is mentioned, temperature is concerned, for temperature, because you have cooled sufficiently to the container, means once you have pre-cooled, they have stored cryogens to this container. So the rate of heat transfer almost remains same. So that is not operating much, whereas the pressure building is controlled by the pressure relief. Okay, so both the temperature and pressure is maintained.
Okay, okay.
One more
So
question, sir. Sir, hello.
yeah,
Yeah,
please
please.
ask.
Sir, in space vehicles, the fuels used in the space vehicle will be cryogenic fluid. Is it, sir? So like liquid
Sorry,
oxygen
I
will be used
not,
in space vehicles.
yeah, yes.
In,
Can you
uh,
please repeat the question again?
yes, in space vehicles, liquid oxygen will be used as a fuel and with other cryogenic fluid. So what is the storage
Yeah.
technique which is used, and also transportation is done to combustion chamber in space vehicles?
Yeah, in space vehicles, actually we carry liquid hydrogen in slosh condition, so that more amount of, because hydrogen is the lightest, means less denser compared to all other cryogens. So to increase the volume, they put actually not in liquid form; it's a slosh hydrogen to increase the density, and again it is carried in the special containers which is meant for storing hydrogen. And similarly, this is the liquid hydrogen is for fuel, and liquid oxygen is taken as the oxidizer, and both is taken in liquid form, and you are having a separate pressurizing system to pressurize this liquid which goes to the combustion chamber. But before going to the combustion chamber, if you have carefully observed, there is a in the outside where this exit of these craft wells occur are the burning and the combustion chamber profile you see it's a actually well-shaped structure, and in that you are having grooves through which this liquid cryogens pass so that it comes to vapor condition before going to the combustion chamber.
Yes, thank you, sir. Thank you.
I think
If the participants wants to ask any question, you can just unmute yourself and ask the questions. Okay, hope there is no questions. Okay, now we are at the end of day 3 of this 6-day FDP. I express my heartfelt gratitude to the speaker, Dr. Upendra Behera, for engaging this session and sharing his insights and experience on the need for cryogenic storage and transfer systems, its design aspects, installation of cryogenic systems, also on the developing of the transfer lines, and also we have discussed about some of the studies on development of these transfer lines. It was really a very interesting session, sir. On behalf of Kurk Institute of Technology and all the participants, I thank you for your precious time and knowledge sharing, sir.
Yeah, thank you. It is a pleasure. But sorry for the delay in starting this session.
It's okay, sir. Yes. I kindly thank all the participants I kindly request all the participants to fill the feedback form for day 3, share in the chat box. I'd also like to thank all the participants who have joined in this session. Please do join for tomorrow's session at 10:30 a.m. and Vortex Tube, once again by Professor Upendra Behera. So signing off till then, thank you. Thank you one and all.
Yes, sir. Okay, sir. Thank you. Thank you. Sir, are you there? Upendra, sir?
Yeah, please tell me. I was about to leave. Yes, please tell me.
Yes, sir. Okay, sir. Tomorrow we'll start at 10:30, no, sir? Morning.
Yes. 10:30 will start, and again I'll come to the lab instead of staying at home. I think the Zoom was a little problem. Okay, no problem. Okay, thank you.
Sir. Thank you so much. And dear participants, please participate. Attend the tomorrow session exactly at 10:30. It will be delivered by Professor Upendra Behera, sir. Thank you, one and all. We are going to end this meeting.